All right, so you wanted to explore how we really know the Earth's shape, right? Well, we've got a deep dive that throws a curveball, literally. Someone's proposing some seriously hands-on experiments, and they're calling it Force the Line.
It's fascinating. Really fascinating. Because it goes beyond just those theoretical arguments about, flat Earth versus globe Earth.
Yeah.
This proposal lays out tangible experiments, ones anyone could try to replicate, with enough resources, of course.
Exactly. We're talking about real-world measurements here. That's what makes this document so intriguing, honestly. The author, Aaron Angers, he's not just like throwing out ideas. He's really passionate about finding definitive visual proof.
Yeah, it's almost like he's saying, let's just stop arguing about complicated models and just see what happens when we stretch a line really, really far, like super far.
So let's unpack these experiments. The first one, okay, involves submerging a 6-mile-long rope in a calm lake. You might be thinking, wait, why underwater?
Well, that's the clever part. By submerging the rope, they're trying to minimize the effects of refraction, that bending of light that can sometimes distort observations. It's been a major point of contention in past attempts to measure Earth's curvature.
Oh, okay. So if the Earth is curved, even a super strong rope pulled taut at that distance, there should be a measurable sag in the middle, right?
Exactly.
Yeah.
And to make sure it's really accurate, they're not messing around with the equipment. We're talking, high quality calibrated equipment across the board. Like think heavy duty anchors and winches to precisely control tension, even buoys for safety. It's a massive undertaking, to be honest, all designed to minimize error and produce reliable results.
Yeah. I can only imagine the logistics of getting all that set up. It would be visually stunning even before you factor in the results.
Absolutely. Just picturing this miles long rope stretching across like a serene lake.
Yeah.
It's captivating, even without knowing the outcome.
Okay, so that's measurement number one.
Mm.
What about the second experiment?
Well, that one involves building a wall along a mile of still water. And the goal is to create a perfectly level line along that wall.
Hold on. How do you even guarantee a perfectly level line over, like, that distance?
Well, that's where the meticulous setup comes in. They're starting with a plumb line for absolute verticality, and then meticulously extending that level line using a calibrated meter stick for the entire mile. It's almost like an ancient surveying technique, but with an incredibly high degree of precision.
And the idea is if the Earth is curved, that line, even if it starts perfectly level, it should deviate upwards as it extends along that, like, mile-long wall, right?
Right. The deviation might be tiny, but with careful measurement, it should be detectable. And that's what makes this proposal so compelling. It's a simple concept, but potentially a very powerful way to visualize Earth's curvature, or, lack thereof.
Now, you mentioned this idea of measuring Earth's curvature isn't totally new. This proposal actually references some historical examples, right?
It does. One of the most famous is the Bedford Level experiment. It was conducted like multiple times in the 1800s and early 1900s along, long straight canal. They were trying to observe curvature using telescopes across the water.
But I've heard the results were, like, all over the place.
Exactly. That's the challenge with these long-distance measurements. Refraction, atmospheric conditions, even tiny errors in the setup can, really skew the results. And that's why this force the line proposal is so intriguing. It aims to minimize those factors as much as possible.
So in a way, they're trying to be like the definitive experiment, right? The one that settles the debate once and for all.
Yeah, and that's what makes it so fascinating. Whether you go into this believing the Earth is, flat or round, it forces you to confront the question, how do we know what we know about the Earth's shape? How much of it is based on what we're told, versus what we can observe and measure for ourselves?
That's a great point, actually. It's easy to take things for granted, especially when it comes to something as, fundamental as the shape of our planet.
Absolutely.
Mm-hmm.
But this proposal reminds us that even seemingly settled knowledge should be open to scrutiny and rigorous testing.
And that's where these historical examples come in handy. They show us, like, what's been tried before, what worked, what didn't, and what challenges Force the Line will need to overcome.
Speaking of historical examples, there's one that's particularly relevant to the Force the Line approach. Back in 1896, a surveyor named William Einbach, he made incredibly precise linear measurements across the Utah Salt Flats.
Okay, so how does that tie into a proposal about measuring Earth curvature?
Well, those measurements, even though they weren't specifically designed to prove or disprove Earth's curvature, are still considered incredibly accurate even today. They actually form a foundation for, our modern geodetic survey,
Mm.
which is how we create accurate maps and models of Earth's surface.
So even back then, people were using like direct physical measurements to understand the Earth's shape.
They were. And those measurements, later confirmed by modern technology, show that careful observation and precise measurement have always been crucial to our understanding of the world around us.
It's like this force the line proposal is like tapping into that long tradition of observation and measurement, but with, a modern twist and a very specific goal in mind.
Exactly. It's taking those the foundational principles and applying them to one of the most fundamental questions we can ask about our planet, really.
Right.
What shape is it, really?
And that brings us to some even more recent attempts to answer that question. This proposal mentions a particularly ambitious experiment conducted by a group called FE Core, who, let's just say, are very passionate about proving the Earth is flat.
Right. They conducted what they called the greatest laser experiment in history, claiming to show inconsistencies with the current geodetic model. That's the model we use to define Earth's shape and location. Kind of like a global map agreed upon by scientists and used for things like GPS. It's known as WGS-84.
But there was a lot of pushback from the scientific community, right? Something about refraction distorting the results.
Exactly. It became a classic example of how interpreting evidence, especially when dealing with something as tricky as refraction, can lead to vastly different conclusions.
So it seems like refraction is like the biggest hurdle in all these Earth measuring experiments, right? And that's why Force the Line is trying to minimize it by, submerging the rope.
Yeah, that's a key part of their strategy. But here's where it gets even more interesting. Remember Kevin Samuel, what we discussed last week?
The guy who's always testing out, unconventional theories. Yeah, what about him?
Well, just this past summer, he did a small-scale test of this Force the Line method in Austria. He used a carefully calibrated, neutrally buoyant fishing line stretched across like a 2.68-kilometer distance.
Wait, a fishing line? That doesn't sound very scientific.
Well, it was more of a preliminary test just to see if the concept had merit.
Yeah.
And the results were, to say the least, intriguing. The standard geodetic model, the one that assumes Earth is, a specific shape and size, predicted a 14.1 centimeter sag in the line at that distance.
Okay, so what did he observe? Did the line sag?
He observed no change, even after applying 6 kilograms of pull.
Wow, that's a pretty significant result, even if it was just a small-scale test. Could this mean that the full-blown Force the Line experiments might yield similar findings?
It's a possibility that Aaron Angers, the author of the proposal, is clearly excited about. And that's what we're going to explore next. What are the potential implications of these experiments, both for science and for, our understanding of the world around us? That small-scale test with the fishing line, it really does raise some eyebrows, doesn't it? It's just one data point, but it definitely makes you wonder what would happen if they scaled it up to the full 6 miles.
It's like that fishing line test. It's like throwing down a gauntlet, Suddenly this proposal isn't just like a thought experiment. It feels like we're on the verge of a real discovery, one way or another.
And that's exactly what Aaron Angers, the author of the proposal, emphasizes. He argues that these experiments have immense value, regardless of the outcome.
Okay, so let's play it out. If the results, confirm the standard model, Earth's curvature as we currently understand it, then what does that mean?
Well, on a practical level, it reinforces scientific principles, right?
Yeah.
And provides a powerful educational tool. Imagine classrooms across the world using this experiment to teach students about, experimental design, data analysis, the challenges of controlling for variables like refraction. It could make scientific principles tangible and exciting for a whole new generation.
That's a fantastic point. It's not just about proving something we already think we know, right? It's about making science accessible and engaging, showing people how we arrived at that knowledge in the first place.
Precisely. But, of course, it's the what if they don't scenario that really gets the heart racing. You know what I mean? What happens if those lines don't curve as expected?
Yeah, that's the part I keep coming back to be honest. What would it mean for our understanding of the world if these experiments they showed no curvature?
Well, it would mean a whole lot of head scratching, that's for sure. Scientists would have to, reevaluate some fundamental assumptions, and it wouldn't just be about the shape of the Earth either.
Wait, what do you mean? What else would be affected?
Well, you see, our current understanding of gravity, right?
Mm.
It's deeply intertwined with the concept of, a spherical Earth. It's what explains like why we stick to the ground, why objects fall at a certain rate, why planets orbit the sun in the way they do.
Okay, so if the Earth isn't like a sphere, or at least not curved in the way we expect, then our understanding of gravity, it might need some tweaking.
Exactly. Wouldn't mean gravity itself is, wrong, but our models of how it works, how it shapes the world around us, might need to be revised. It would be like a monumental shift in our understanding of physics.
So it's not just about like maps and globe. It's about the fundamental forces that govern the universe. This proposal is starting to sound less like science and more like science fiction.
It does have that mind-bending quality to it, doesn't it? But remember, we're still talking about the scientific method here: observation, measurement, analysis. These are like the tools we use to understand the universe, whether the results are expected or not.
So even if these experiments, throw our current understanding into like chaos, it's not a failure of science, right? It's an opportunity for science to adapt and evolve.
Precisely. It would usher in a period of like intense research and debate, with scientists scrambling to come up with new theories and models to explain these unexpected findings. It would be incredibly exciting.
I can only imagine the headlines. Earth flat, gravity broken, scientists baffled.
Something like that. But before we get too carried away with these hypothetical scenarios, let's come back to the proposal itself. Aaron Angers doesn't just lay out these experiments. He also proposes some pretty ambitious next steps.
What kind of next steps are we talking about?
He's calling for expanding these measurements to, even greater distances, trying them in different environments, and involving independent verification teams. It's about rigor, transparency, and ensuring that the results, can be replicated and scrutinized by the wider scientific community.
So it's not about, just doing one experiment and declaring victory. It's about a sustained, collaborative effort to get to the bottom of this.
And that's what's so refreshing about this proposal, honestly. It's not about dogma or proving one side right and the other wrong. It's about, the pursuit of knowledge, the willingness to question, and the courage to follow the evidence wherever it leads.
It's like saying, okay, let's put our assumptions aside and just, see what the universe has to tell us.
Exactly. And that brings us to an important question for our listener. Why should you care about all of this? You might be thinking, well, I've got GPS, satellites, countless images of Earth from space. Why does it even matter if, like, a rope sags in a lake or a line deviates on a wall?
It's a fair question. What would you say to someone who's wondering, why this matters to them, even if they're not a scientist or a surveyor?
I'd say it matters because, it goes beyond just the shape of the Earth. It speaks to the very core of, like, how we acquire knowledge, how we build our understanding of the universe. It's about the importance of, critical thinking, of skepticism, of not just accepting what we're told, but demanding evidence.
Especially in a world where, misinformation spreads so easily, those skills are more crucial than ever, I think.
Exactly. Think about it this way. If we're willing to, like, question something as fundamental as the shape of, our own planet, then we're better equipped to question other claims and assumptions, right? To discern fact from fiction, to make informed decisions based on evidence rather than, blind belief.
So it's not just about, the shape of the Earth. It's about developing those mental tools to navigate a world overflowing with information, much of it, unreliable.
Precisely. And that's why these force-the-line experiments, regardless of their outcome, hold such profound significance. They remind us that science isn't about, like, clinging to old ideas, but about constantly testing, questioning, and refining our understanding of the universe.
It's about being open to being surprised, even if those surprises, shake the foundations of what we thought we knew.
And sometimes those unexpected discoveries lead to the most profound breakthroughs. Who knows? Maybe this proposal will spark a revolution in our understanding of the universe, or
Wow.
maybe it'll simply confirm what we already thought we knew.
Either way, it's a journey worth taking.
Absolutely, and that's what we're going to delve into next. What would it feel like to, witness these experiments firsthand? What would it mean for us, not just as, as scientists or thinkers, but as human beings to confront like such a fundamental question about the world we live in?
It's amazing to think that we could actually be on the cusp of these experiments, like really happening. Imagine being out there on the lake, watching that 6 mile rope just, disappear into the distance.
It would be like something out of like an adventure novel. And then like the tension builds as they start, taking measurements. Is there a sag? How much? Does it match what we expect based on, our current understanding of Earth's curvature?
Yeah, I can practically like feel the anticipation. And what about that mile-long wall? It would be like an ancient monument to scientific inquiry.
Picture this. You're standing at one end, looking down this perfectly straight wall, stretching, as far as the eye can see. And then like with meticulous care, they start checking for, any deviation from that perfect level. Every millimeter matters.
It would be a powerful reminder of like the precision and patience required in scientific observation. There's no room for guesswork here.
And imagine the collective gasp. If the measurements show something, something unexpected, it would be like a moment of truth.
Yeah.
A challenge to our most fundamental assumptions about the world.
And that brings us back to you, our listener. What would you do if these force the line experiments yielded results that, contradicted everything we thought we knew about Earth's shape?
Would you cling to your existing beliefs, or would you be open to, revising your understanding of the world? It's a question that goes beyond science and
Yeah.
touches on like the very core of who we are as human beings, really.
Are we willing to embrace the unknown, even if it challenges our most, deeply held convictions?
That's the beauty of science, isn't it? It's a process of continual discovery, of questioning and revising our understanding based on new evidence. It's not about like being right or wrong, but about getting closer to the truth, even if that truth turns out to be, stranger than we ever imagined.
So in a way, these force the line experiments, they're a test, not just of, our scientific knowledge,
Yeah.
but of our like intellectual flexibility and our willingness to adapt.
Yeah, and that's a lesson that it extends far beyond the realm of science, right?
Yeah.
It's relevant to every aspect of our lives, from how we make decisions to how we interact with with the world around us.
If we can approach the question of, Earth's shape with open minds and a commitment to evidence, then imagine what else we can achieve.
It's a reminder that curiosity, skepticism, and a willingness to challenge assumptions, these are essential tools,
Yeah.
for navigating the complexities of the 21st century.
And that's something we can all, strive for, regardless of our beliefs about the shape of our planet.
So the next time you look up at the night sky or gaze out at the horizon, remember those who dared to question, those who sought to measure and understand the world around them.
Their legacy lives on, not just in the knowledge they uncovered, but in the spirit of inquiry they embodied.
That spirit is within each of us, waiting to be, awakened.
Thanks for joining us on this deep dive. We hope it sparked your curiosity and inspired you to keep questioning, keep exploring, and keep learning.
And remember, the universe is full of wonders,
Yeah.
both known and unknown.
Until next time, keep those minds open and those questions coming.